now the carts too?
So this is the thing that I want you guys to know is that up until now, because our objects weren't really free to rotate, we just always shrunk them down to a dot at the center of mass.
So like our carts, for example, the wheels on that were free to rotate.
Right? But we just assumed it was just one small, infinitely small particle.
So,
And
but
now, we're not.
now if we do another cart problem, do we have to look at it as a bigger?
We don't. We could, but we don't. The thing about the carts is that they make the wheels really small and very light, so they don't have very much rotational inertia.
So we're just, okay, so in a cart problem.
Don't worry about it for carts. Unless it says a cart with heavy wheels.
Oh, come on.
Listen, I'm not charging things. Any other forces, Claire?
Friction.
Are you sure?
I mean, you didn't say it was frictionless.
Now, this is the thing, and someone mentioned this yesterday. If I just put this on here and let it go and there was no friction, what would it do?
Just slide.
It would literally slide down.
That'd be sweet.
So, what does friction do to the ball?
Let's it rotate.
Torques it.
It lets it
Thank you, Ryan.
push off.
Yeah, I was going to say it causes it to roll, right? It causes it to roll. Without friction, it would just slide.
I can almost see it.
I don't have a frictionless track, sorry, man.
Get some butter.
Get some butter. So, where is the friction applied and in what direction?
Surface of the ramp, up the ramp.
Up the ramp from where?
The
point of contact.
There you go, point of contact.
Oh. Yeah.
That is correct.
Mr. Bennett,
Yes?
so friction like opposes movement, right?
No.
Or opposes other forces, I guess.
So, those are generalizations that we use
Yeah.
before we have a really good sense of the complexities of these things.
Okay.
So friction is an anti-sliding force, and it will apply a force in the direction that the two objects interact in. It doesn't really oppose motion, but in certain circumstances it does. If I just push a block across the floor,
Yeah.
the block is sliding one way and the friction is back, correct? And that we understand because the box was moving one way and the surface was pushing it back. Okay? Even if I let a box go from rest, the force is in the down direction, so the friction is back.
Yeah.
Each one is situated.
Okay.
Okay? So this one, it would slide, but the friction is there, but it causes a torque. Right? Alright, so here's a question.
Oh, it's because of the torque counter, clockwise.
We have three forces. This is great, by the way, BT dubs. Very nice. Okay? Which of these forces, could be all of them, could be none of them, causes a torque on the ball? Check your neighbor, meow. Which of these forces do you think causes a torque? Check your neighbor, meow.
And that's why it rotates.
Say,
NG, it has no radius, and force normal, it's angle between the force and the radius is 0. Sine is 0.
Yeah,
That
so
torque would be 0, and the torque would be 0 because it's got 0 radius. Force of friction, it's at that 90-degree angle, and it has radius, and it has a force. So that's going to be some positive force values.
and that's why it rotates counterclockwise. Or anti-clockwise.
I'm not sure if it's positive or negative. It's more than 0, I guess.
Hold on, so
definitely.
So why is, I get it, but why is it
They can still hold the same
Well, they were like, what's the
and lighter.
More
What's your grade? 12%.
it's R.
Every problem is
It's
taken.
FR sine theta.
Yes, sine of theta would be 0.
Oh, because it's at a 0-degree angle
Yeah.
from the.
Alright, you guys ready? Which of these supplies a torque?
Force friction?
So, remember, torque has to be R cross F, which means there has to be a center of rotation, or an axis of rotation, which we're going to use the center, because the ball is rolling around its center. Is that cool? Sorry. There has to be a force, and it has to be some distance from the axis of rotation. True? And the angle right? You need to have some angle between these two things. Yes? You with me on that?
Yeah.
All right. Does the mg supply a torque?
No.
No,
No. How do you know?
radius
Because
is
it's
0.
at the axis.
Good. So for the mg, we're using the center of our ball here as our axis of rotation. The mg doesn't even have a radius, right? Is that cool?
Yeah.
Does the normal force supply a torque?
Nope.
No.
Why not?
Well,
Same.
no, it has a radius, but the sine of theta is 0.
Okay, I'm with Simon on this one. If I look at this, okay, I'm going to do it in green. If I draw the r vector, okay, you guys see that r vector there? It's drawn from the axis. It's drawn from the axis of rotation to the place where the force is being applied. So there is a radius there. Thank you. But let's look at the direction here. Let's look at the direction of these forces. The normal force is up and to the right. The radius vector is down and to the right. Those two are this way. You know what we call that when they're in opposite directions? Anti-parallel.
Oh my god.
Okay?
Did you just make some of this stuff up?
No, man. This is-
Anti-clockwise.
I prefer counter parallel.
So, but the thing is, if they point like this, what's the angle between them?
0.
This angle is 0.
180.
What's this?
180.
It's 180. And what's the sine of 180?
0.
0. So you can't. What's up? Are you done?
Yeah.
Okay. Sorry, Ash. Thank you so much. Ooh. Does the friction supply a torque?
Yes.
Heck yeah, it does.
Heck yeah.
Okay. That's R sine theta, yeah? Is that cool? And in this case, what do you notice here about the angle between these two?
It's
No, you got a Chevy.
Is that cool?
yeah.
Guys okay with that? So, this is going to be here, so then I would say that the torque basically it turns out that the torque here is just the radius times the friction, which is interesting because this ball is rolling down, right? Okay, so far so good? Now, when I said that rolling was a combination of translational and rotational motion, we have a good handle on the rotational here, yes? But what about the, sorry, I'm super like, too much stuff in my brain today, too much stuff in my brain.
We need a brain break.
We do not, we literally just started. What about the, is the ball accelerating down the ramp in a translational way?
Yes.
Yes, it is. So do you think the forces are balanced or unbalanced? I would say the forces are unbalanced. So let's talk about that. Okay. How do you express the net force?
Mass times acceleration.
Okay. Oh, totally, but I'm like in terms of diagram, right? Is it a ramp?
Yes.
Yeah.
What direction is the acceleration?
To the right.
Down.
So since the acceleration is down the ramp, what am I going to do with my axes?
Oh,
I'm going to rotate them, okay? I'm going to rotate my axis so that it is accelerating in the direction of motion. I'm sorry, it's accelerating in this x direction so that, right?
Yeah.
So now, I'm going to have to break this up into its component parts, which is something you know how to do. This is why we did so many ramp problems earlier this year.
Let's go.
So tell me about my net force in the x direction.
It would be, what, it would be M, no, not MG, I'm sorry. It'd be force normal or, force normal sine of theta minus force?
Nope, it's this is mg sine.
Oh, that
theta.
is mg sine of theta, what am I saying?
I don't know.
mg sine of theta minus force of friction.
Good, we got that there.
Oh,
Oh, I switched to a little f instead of ff. I don't know why. That was weird.
Oh, I thought you did this. Oh, yeah.
That's friction.
Yeah.
Okay, thank you. I appreciate that.
Will that be clear on like an AP test?
Yeah, you can label it however you want. Doesn't
Yeah,
matter.
okay.
Is that a good statement up there?
Yeah.
Is that cool?
Yeah.
All right, so I'm okay with that. How do we express the net force in terms of Newton's second law,
That equals E times head.
Yeah.
right? So I would say that the mass times the acceleration is equal to what?
Mg sine theta minus.
Does that make sense?
Yeah.
Is that cool with you?
So. Okay. It's weird that we're counting the force of friction as torque in translation.
I know, that's what rolling is, man. All right, now, we need to take a step back because I'm okay with this statement, but here's the thing. This is Newton's second law for translational. What's Newton's second law for rotational?
Oh.
Jesus fish
Yeah.
is equal to what?
Jesus. So the net torque, instead of ma, it's
Oh, inertia.
I alpha, right?
Yeah.
You guys see how these are the same kind of statement? That net force is equal to mass times acceleration, so net torque is equal to moment of inertia times the angular acceleration. Because is it accelerating angularly? Yes, it is. It's speeding up the amount that it's spinning.
So, just out of curiosity, like, is that equation you just wrote, like, still credited to me?
Yes.
Okay.
Yes, this is all him. How many torques do we have?
Lots.
How many torques do we have?
One.
Just one. Just one torque, right?
Yeah.
So this is the net torque then.
How do you know how many torques you have?
Yeah.
Because we had three forces, two of which we decided weren't torques because they can't cause rotation.
Yeah.
So only the friction can cause rotation.
Oh, okay.
So,
So wait, how'd you get from torque net inertia to Jesus fish to
Since this is only one torque, so this is the torque on here, and since this ball only has one torque on it, this is equal to the net torque. You know, if you only have one force on an object, then that is the unbalanced force.
Oh, so then inertia and Jesus fish is equal to R.
There we go.
I'm gonna forever call it Jesus fish.
Okay. So we're going to set those equal to each other, just like we did that over here. And now what's interesting is I have this as an idea. I know that I have this up here. Okay? If I wanted to solve for the acceleration using that one over there, what would I need to know? I would need to know the friction, true?
Yeah.
But I don't know the friction.
But if you know your radius, you.
But if I come down here, is there a statement for friction down here? There is, right? So,
Oh, I see.
this is how this works, and this is really interesting, okay? In order to get this, we need to take one step back, right? As this ball rolls, we know that if you were looking for a spot on the ball, one spot on the ball as it rolls would be equal to the angles that it goes through times the radius, true? Right, we talked about that. That's on anything that's spinning, right?
Yeah.
This translates to, if I wanted to find the linear velocity, I would take the angular velocity times the radius. Okay? And then, what's the third one down then? If you want to calculate the linear acceleration, what would you need to know?
What is that actual symbol called again? I keep thinking it's.
So, this is alpha, that's the
Oh,
Greek letter
alpha.
alpha, that's the angular acceleration.
Where did you get those three red equations from?
they know from. So if I spin a wheel, okay, if I spin a wheel, so this is my radius, true?
Oh my god.
Okay?
Right, I
Fine.
know exactly how you got this.
You're good. If I spin my wheel, all right, and I spin it a certain amount, so this point here on the end rotates around this curve, let's say this much. Okay? This distance, okay, this is actually how far you went in a linear way. If you're an ant crawling on an apple, you don't know you're going around a curve, right? So this would be your linear distance if you were an ant. But if I draw from here to the center, isn't this also a radius? Okay? And then